just want to go over this acceleration formula, and just so you have just can look at this after a test or something like that. So far we've done velocity problems where the velocity is constant. Now what we're going to do is we're going to add acceleration to the mix. So you see these vehicles driving here. What you'll see is one is slowing up, slowing down. So you got different accelerations, and that's what we're going to see. So our basic acceleration formula is the change in velocity divided by the change in time. Okay, so we have this change in velocity divided by this change in time. And we can solve problems that deal with velocities that have either a starting or stopping, or you're at rest, or you're decelerating, things like that. Okay, and then we can also add distance to this, but we'll get to that in a second. So constant acceleration is when it's non-changing acceleration. That's just when you're basically on cruise control. In other words, it comes down and it's a linear slope of a velocity versus time graph. Okay. Accelerations we deal with are all in constant forms. Okay, so here's my delta V and my delta T. So let's take our original formula, and now let's change this little delta V here. So now we have the final velocity, that's what VF stands for, and the initial velocity, that's what VO stands for. Delta T is the change in time, and A is the acceleration. Okay, we can get rid of that because time is just time, it's a total. Okay, and generally it's because it's a single number. And so if we want to solve for the final velocity, what we just do is we just do a little formula manipulation. We're just going to flip this real quick, and then I'm just going to add the VO to both sides, and I get VF equals VO plus AT. So simple formula manipulation will get us what we need. Now instead, we can take a look at this formula. Now all these formulas are on your sheet in their base form, but what we're going to do is we're going to do a simple manipulation of those formulas. Okay, so here look, I have D, and I could solve for that. So a lot of times we're asked to calculate the formula, calculate the distance using the formula. Instead of going through a formula manipulation, which would definitely explode your brain, let's just look at the formula itself. So VF, VO, and T, here's a formula. Notice there's no A in this formula, and what you're going to find is all these formulas will be missing one of the 5 things you need. So distance, acceleration, final velocity, initial velocity, or time. And you have to have 4 of the 5, or be looking for 4 of the 5. One will be missing, and that's fine. We'll just solve for that. So here, if you have VO, A, and T, you can use this. But the critical point for this is you have to list what you know. Okay, and then you got to be able to pick the formula where you list what you know. Okay, it's like a treasure hunt, and you should be able to find the formula that you're missing. So problem 1. A Saturn rocket carried astronauts to the moon and accelerated at a rate of 17.0 meters per second squared at takeoff. What's the velocity achieved when the rocket reaches an altitude of 1,500 meters? So let's figure out what we know. Okay, so we know we have an acceleration. So accelerations always have the formula meters per second squared. Okay, we know we have a distance. We actually know what our initial velocity is because it is starting from rest. Okay, what we don't know is the final velocity. What's the velocity achieved when the rocket reaches 1,500 meters? So let's figure out what we know. We know our acceleration, we know our initial velocity, we know our displacement or our distance, and we have to know our final velocity. So now we look through our formula sheet to pick a formula that has all of these variables. And when we do that, we find this formula. So now we just plug our values in. We don't know VF. We do know this. That's a constant. A is 17.0 meters per second, and D is 15. Okay, so we're going to plug all that in, and we're going to get this. We're solving for VF, not VF squared, so we're going to take the square root of both sides, and we're going to get 226 meters per second. 3 sig figs, the smallest number there. This 0 doesn't count, it's exactly 0, so it doesn't count as a single sig fig. So Janina's driving through a school zone 30 kilometers an hour. She needs to stop. Her brakes produce a deceleration of negative 3.40 meters per second. Calculate her stopping time. So she has to come to a stop. So we know her final velocity. Okay. What we want to look for is how long is it going to take. Okay, we're looking for time loss. We're calculating her stopping time. So notice our acceleration here is negative because we're slowing down. So that's an arbitrary negative you have to put in. We know our velocity is 30 kilometers per second. Now here's one of the problems. We have kilometers per hour. We have kilometers per hour and meters per second squared and meters per second. We're going to have to convert this into meters per second. Don't make the mistake of plugging this value in because all the units have to be the same. So first thing we got to do is we're going to convert this kilometers an hour into meters per second. And instead of 30 kilometers an hour, we're going to get 8.33 meters per second. We're then going to find a formula that fits all this. Here we go. We're looking for time. So I'm going to subtract the VO and divide by A. Okay, so I subtracted the VO divided by A. Fairly simple algebra. I'm going to plug in my values. And I'm going to get 2.45 seconds. So this is the table that you'll use, and this is in your workbook as well. And you can just figure out, okay, I have all these, or I'm looking for 3 of the 4, or I'm looking for 1 of the 4, but D is not mentioned at all. I'd use this formula, and et cetera, et cetera, et cetera. Okay, so this will help you hopefully figure out which formula to use. So free-falling objects, you have an acceleration that is now dropping, okay? And the acceleration due to gravity on Earth is negative 9.80 meters per second squared. So this number, it's on your formula sheet, but it's a negative value. So you're dropping a sheet of paper or pencil, you're repeating this, so we'll do this in class, but you're going to be able to see this same rate falling. So we call this free-falling acceleration due to gravity. We give it the symbol G or AG, generally G. And near the Earth's surface, it's said negative 9.8. And it decreases as you get further and further away into space. The pull from the Earth becomes less and less. And it's always negative for a downward object. So here I have an elephant and a coin. Notice that they fall at the same rate. The acceleration is the exact same throughout. Okay, doesn't matter if it's heavy because we're going to ignore air resistance. So mass has no part of this. So one of the things you should know is when we do this idea of throwing a ball up or throwing a ball down or dropping a ball, just realize that when it goes to its starting point, the displacement as a ball goes up and down, this whole displacement is 0. Okay, and we can split these pieces in half. But the real key to this is knowing that if we're using it up, if we're throwing something up, it's positive, and if we're dropping it down, it's negative. Okay, so that piece of understanding that when we throw something up, sorry, I'm just getting a pen here. When we throw something up this way, it's going to be positive. Okay, when we're going this way. When it's dropping back down, it's negative. And then the overall displacement, if it started here and ended here, is going to be 0. Okay, that's really important for you to understand because that will be in some problems. I hope that helps, and come see me if you have any problems with these questions.